So we're looking at page 70 in the Unit 3 packet. We're talking about inference for a one-way table, specifically chi-square distribution. The assumptions for this hypothesis test is that the sample simple random, or it is a simple random sample. It's some sort of skewed distribution, or not necessarily a normal distribution, and that you're testing for homogeneity, independence, or goodness of fit. Right? That'll be in the framework of the problem. So that seems a little daunting, but that's that'll be stated clearly in the problem. It'll be very easy to recognize when you're dealing with a chi-square distribution. The advantages to this distribution are that we're not just limited to two populations anymore. We could have three or more populations that we are comparing to one another. And another advantage is that it's always right-tailed, and it only uses positive values, which takes out the guesswork associated with the alternative hypothesis. It's always right-tailed, and so that simplifies things. Right? So your distribution ought to look something like this. Now, I included the table of values here because I'm gonna show you on Desmos, but the table of values is the kind of thing that doesn't really change too much depending on the problem that you're working on. Right? So it's a pretty handy reference, so I figured I would just leave it in. And it's a little old school, but why not, right? So we have our x and y axes. X-axis starts at 0. You're going to have some sort of right tail associated with the alpha value. That's going to give you a critical value. That's going to be represented using the variable chi-squared. All right, so it's kind of like a funky x. And then you're going to have some sort of test statistic based on the data that you're working with that's either going to fall in the shaded region or not. All right, so whether it falls in the shaded region or not will dictate whether you reject the null hypothesis or not. Fortunately, in terms of null and alternative hypotheses, you're limited to these three possibilities. All right, so there's less and less guesswork as we go on. Your null and alternative hypotheses are either going to be independence or dependence, or you could say independent or dependent. Good fit for a population distribution or not a good fit. Or all the population proportions P are equal to one another. The alternative to that would be at least one is different. Right? Because if you have multiple population proportions and there is a difference among them, it doesn't mean that every one of them is different to every other one of them. It could be the case that, like, let's say you have five populations, four of them could be equal to one another. It's the fifth one that may be the oddball. All right, and so that's what we're going to kind of try to identify. All right. In terms of a procedure, very straightforward. Choose the level of significance, or it'll be given to you in the problem. Determine the critical values using the table above, based off of the degrees of freedom. Degrees of freedom is equal to k minus 1, where k is the number of categories. And then we have a formula, a good-looking formula that we'll have to use. All right, Desmos will be a good resource when it comes to this. I'll just do a quick copy job so I can have that on the next page. All right, a quick abbreviation to it is the sum of O minus E, observed minus expected, squared over E. All right, we'll get to that in a minute. And then if the value of the test statistic falls in a rejection region, you reject the null, otherwise you don't. And then we state our conclusion in words. All right, so I'm going to hop over to page 70, where we talk about rolling a die 60 times. So we roll the die 60 times, and we get this distribution. And you can see it's very clearly labeled observed, so the O's, and the expected, the E's. All right, so if we just do a quick sum of our observed values, and we just pop that into a list in Desmos, 14, 15, it'll try to auto-populate 16, but I'll put in a 10, 8, 7, 6. I don't need an extra cell. One way to do this very quickly would be to go to functions. Under stats, you can grab total. Total of x1 would be 60. Right? So the sum of this column, or, well, column in Desmos, row on paper, the sum is equal to 60. Good to know, because if you roll a die 60 times, you probably expect there to be about 10 of each outcome, right? Because it's a uniform distribution. Way back in probability, we talked about that. A uniform distribution, equal chance for each outcome, right? So it should be 10 per outcome to give you a total of 60. That's not what happened. What we want to do, based off the question, does this die, does this data cast doubt on the fairness of the die at the 5% level? It's just basically asking, okay, do these outcomes, like if you're playing a game of chance and maybe you lost that game of chance, is this enough evidence for us to say, oh, there's something fishy going on here? All right. So the null and alternative hypotheses would be that all these probabilities should be equal to one another. I'll take it as a typo. This box is a little on the short side for what we need. I'll make it a little longer. Probably could have just hand drawn it quicker, but you know how it goes. All right, so the null should be that the probability of getting a 1 is that is equal to the probability of getting a 2, 3. That's not a 3. 4, 5, 6. Trying to squeeze it in there. All right, the alternative is at least 1. At least one of those probabilities is different. All right. So what we need to do is figure out our chi-square test statistic. All right. So we'll copy paste. Oh, I copied it from the previous page, but then I lost it. All right. Well, I'll just rewrite it. Chi squared is equal to the sum of O minus E squared divided by E. They gave us the alpha value of 0.05. The calculator test is a chi-square. We just used a little notation there. In terms of the graph, we could just get that from Desmos. I'll show you how to do that in a couple minutes, but let's crunch these numbers real quick. So in the first column, we know that the x1 values are corresponding to the observed. So let's get our expected values into the y1 column. Now you can, if you want, I'll just show you real quickly. If you wanted to, you could retitle this. The problem is you want to do that before. Oh, I was going to say you want to do that before you type in the data, but it looks like you don't have to. All right, so O and E. I think in the past I just tried doing it that way and then panicked once it wiped out the entire column, not believing that it would actually show up again. But now what we can do is we can just do a quick division, parentheses. I use capitals, so I got to make sure I continue to use capitals. O minus E, close it up, square it, divide by E. All right, so that'll give me all the computations I need. All right, and if you want, you can tuck that down on paper, but as you know by now, I accept the Desmos work in lieu of handwritten work. O minus E squared divided by E. If you want to just jot them down on paper, at least for the note-taking portion of it, it's not a bad idea, I guess. 2.5, so 1.6, 2.5, 0, 0.4, 0.9, and 1.6. All right, what your test statistic is the sum of all these values. So if I take all these values and add them up, I could do that by hand, or I could use the total function. All right, But the thing is, with the total function, I have to type this in, this whole expression in again. All right, so it's kind of annoying, and you know, like on a touchscreen, it's not copy paste friendly. So I'll just do it real quick. So total fraction O minus E, close it up, square it, divide by E. Now this is a small set of data, so you might look at it and say, well, I'll just add them up, and that's perfectly fine. All right, but what we get here is a chi-square value. Now this chi-square value is notation only. All right, so this is notation. It's not an actual x squared. That's the notation for the test statistic. All right, so we got a result of 7 here, but we need something to compare that to. Otherwise, we can't draw a conclusion here. All right, and so that's where the graph comes into play, and I'll show you that in a sec. This is also a typo because we're not going to use the p-value approach for this. All right, so that should go away. So in Blackboard, if you go into the Unit 3 calculators, you'll see when it says chi-square distribution. You click on that, and this is what's going to come up. All right, this is so that you don't have to use that table on the previous page. All right, so what we're going to do, and I'm just going to draw a rough sketch. Poor quality, of course, because, you know, not that poor. I just want to make it look skewed. All right. Now you can't go by what's there already. What we have to do is account for the given degrees of freedom. Degrees of freedom is the number of categories minus 1. All right. So there are 5 categories. All right. So therefore, k is equal to 5. All right. Degrees of freedom is equal to k minus 1, which is going to be 4. So the first thing I would do, if I'm working from top to bottom, and just take note of the notation here, n is equal to the number of degrees of freedom, so I'm going to make that a 4. All right, changes the shape of the graph a little bit. All right, we want 0.05. Now I set up the calculator to default to something at least in the neighborhood of 0.05. So what you're going to do is you're going to slide your slider until you get as close to 0.05 as possible. All right. Now it takes a little doing, but if you're careful, you'll get it. All right. So I'm debating here. I got 0.0518, 0.0497. 0.0497 is actually closer to 0.05 than the 0.0518. So that's the one I'm going to go with. All right. So what that gives me is the critical value, and you could see it's highlighted on the graph. All right. So let me just kind of bring that in so you see it. It gets a little cut off based off of the nature of the screen, but it's supposed to extend forever. It really does. It just doesn't quite look like it at the moment. But I'm going to have that set up so that I can label it here. So my critical value for chi-squared is equal to about 9.5. All right, so that chi-square value that came back, that's the one that we're going with. The lowest possible value in a chi-square distribution is equal to 0. The degrees of freedom is the number that goes right smack dab in the middle of the hump. So this is degrees of freedom equal to, in this case, 4. And so the test statistic, we came up with 7. So I'm just going to scroll my slider till I get there, and you'll see that, you know, somewhere in the neighborhood of that vertical line, I'll just kind of pop it here, is going to be your test statistic. And that does not fall in the shaded area based on the value of alpha. All right. So, because alpha is 0.05, that creates the shaded region based on my shoddily drawn diagram. And so what we can say here is that we're not going to reject the null hypothesis. So do not reject the null hypothesis. All right, so the null hypothesis is the keeper. The alternative is the goner. So there is insufficient evidence to reject the claim that the population proportion for each outcome of the roll of a die, or the population proportions, are equal. All right, so there's not enough evidence to get rid of that. All right, so there's insufficient evidence to reject the claim that the population proportions for outcomes of the roll of a die are equal at the 0.05 significance level. Therefore, the claim that, all right, so what we do is address the null hypothesis in the first sentence. We address the alternative hypothesis or the question in the second sentence, depending on what's being asked. And so does this cast doubt on the fairness of the die at the 5% level? All right, so that's what they're really asking. It's not really a claim, but we can kind of frame it as a claim. Therefore, the claim that the die is unfair is false. All right, because alternative hypothesis would be unfair. You could also say, therefore, the claim that the die is fair is true. Either way. But the first sentence has to address the null hypothesis.